Today we're going to look at the first of one of the Radar Room's extreme projects. Now, what you call an extreme project? Well, an extreme project we consider as something which is effectively reinventing the wheel. The design has been designed a long time ago, but somebody's come along, felt they don't fully understand it, would like to make it themselves. They don't care whether they're going to do what somebody's done already, but they're going to do it for a better understanding. Now, in this particular example here, I inherited these things a long time ago, and they've been kicking around the loft with all the diagrams and things, and I finally pulled the whole lot out and see if I can make it work. What it does is transmits a video picture over a phone line. In this case it's going to be a twisted pair because there's no modems involved, and it is rebuilt in the receiver side and sent to a monitor. The video being just an ordinary composite video from a monitor. It can be from just about anything that produces a composite signal. It's a monochrome signal, but as most things these days are colour, we have to strip off the chroma, that's the colour signal, and then work on it as an ordinary monochrome signal. This, obviously, the receiver has to generate a standard composite output to drive anything ranging from a TV with a CV in to a small video monitor. This one's quite old, it's a yellow one, but that is what we're using in this particular instance. There's software in it, which is in the proms. This was written in machine code. I have all the machine code listings here. Z80 is transmitting, Z80 is receiving. It is very slow, it is very low resolution, but hey, it works. Clearly, for anybody interested in learning how this happens, we're assuming you have a knowledge of video signals, and not everybody does. So what I'm going to do is quickly run through the sequence of events in here in blocks, and we'll see the thing working at the end of the day. I'll show a few bits of circuitry in a second. If we look at the top of the board, this is the transmitter. So I'm going to rush through this because there's so much to cover, but at least it'll give you an insight into what's involved. Video in, this is where the camera goes in. We have a part here that strips up the chroma and the luminance. They break up the video signal and the picture. There's a little sync stripper here which pulls it off, pulls the sync off the signal coming in, and then splits it off and sends it down the board one way. There's a flash converter here, analog to digital flash converter. Then there's a digital to analog to set the black and white levels, which are something which is part of the video signal. The signal then feeds down into the board. We have 32K of RAM and 8K of RAM. Then we work our way through. There's yet another D2A converter in here, and there's a test LED, Z80 CPU, Z80 SIO, which is the serial I/O for the Z80 series. This is a Z80A, this particular one that's running here, and we have the software for it. That is basically it. There's obviously a lot more involved. We'll quickly have a glance at the circuitry and you'll see what I mean on that one. But now let's have a look at the receiver. Here we have the receiver section. At the top, instead of having a camera in, this is the output to a composite output to a monitor. Go to the bottom upwards. We started with our Z80 and a Z80 SIO. Another test LED here I think was used during development to check it's working. 2K of RAM and 32K of RAM, 2 blocks there, and similar sort of circuitry as we had with the transmitter. It's just a heat sinking for the power splicer. Now this is interesting because there's a 50 megahertz oscillator here and a divider. This is to give us a pixel clock that will give us a steady picture. Once again, it's one of these things that if you go into in detail, you'll find that if you say a 20 meg, you'll see slight jitter. There's a D2A again there. This one here, the only one that sort of is a biggest chip that is specialist is a sync pulse generator, and this is generating sync pulses. So there we go, with similar ICs. There's very few. This last little bit here with these analog transmission gates, CMOS ones, are to generate the video signal. So with the sync pulses coming from this sync pulse generator feeding into this, a little bit of analog circuitry here which creates the video signal, which we then add from the D2A converter here, we add that to it and generate our composite signal. That's about as far as I'm prepared to talk with these. Let's have a look at some circuitry. I think a quick glance at this shows that it would be rather pointless trying to go through the circuit, because this is a bit how I do my circuits as well. One tends to put ideas down as you think of them. There's little odds and ends. It's suddenly there's pink bits. Yes, this is an adjustment, this is an adjustment. These are all trimmers here with the pink on them. Very quickly, this is the transmitter. So the composite signal goes in here. This is a color signal. It goes through a part here that strips off the color. This little device here across that, this LM1881, is generating our vertical and composite signals, which is feeding in different directions. We're coming through here. This amplifier multiplies by 2. There's a 12 meg oscillator here. Look further down. This is the 3300 flash converter. So the video goes in here from here, and now we're into digital. So it's going through an AC244, and this is disappearing out on the data lines. The 4040s, anybody knows their CMOS will know that they are counters, and there's 2 of those which are actually generating the numbers we want to actually generate the lines and the frames. Other side, we can see these buffers, address buffers. There's 32K by 8 of video memory. There it's there, and it's feeding straight in from here. This is the Z80 SIO. There's the ROM and there's the RAM, 8K, 8K. Here we have a data which is coming out, and this is the D to A, so it's D to A converter there. And that is about it. I won't go any further than that. That's the transmitter side. So let's have a quick look at the receiver. Okay, this looks very much like the transmitter circuit. That's starting in the other way. It says in and out here. These are the transmit and receive from the SIO, which is the serial controller, Z80. Well, for this reason, we seem to have only 2K of RAM for the receiver. Obviously 8K of ROM still. There's the video memory up here with 32K by 8. And we have the same interfacing chips for it. So if we go over to this side, this is slightly more interesting, more complicated perhaps. We have here, this is the sync pulse generator, and this is a D2A. So this side is all analog, this side, and this side is all digital. They're telling us that there. Various clocks, more 4040 counters to give us to make up the picture. There's a bit about the 50 megahertz clock driving an F163, which is an old logic series, the F series, but it's supposed to mean fast. And that's it. So that's that. But we can do a bit better than that one, because there is in fact another picture showing us this. And in fact you can see it's been neatly drawn out. This is the sync pulse generator. This is a set of analog transmission gates here with an inverter. ZTX109, which is much the same as a BC109, and that is our video out, and that's what we take to the monitor. So you can see that makes that bit slightly easier to understand. There's a regulator in here, and there's a little bit more vertical line out, blanking, horizontal out. All of these things are video terms. So let's have a quick look at a video signal. Of course, today video has become so much easier. I mean, you pick up your smartphone and take your pictures, and you send a file, and that's it. You've now copied it and send it to your friends. Obviously video signals are much more complicated than that, even with CCD devices like found on modern digital cameras and on things like smartphones and tablets, etc. But this is actually a video signal as would have been around since the 1940s. I'll say once again, I'm going through everything quite quickly just to give you a brief understanding what we're talking about. This is a video signal here with the wiggly bit here, and here we go. Now this part is the picture information. They call it picture detail here. This is a line sync pulse. These ones. There are also frame sync pulses that come a bit further back here. We'll show you those on the scope in a minute. But the line sync pulse, most interesting. In this particular instance, they're talking about it's 4.7 microseconds. That's the width there to give you some idea how wide this is with the 625 signal. The older signals in the 1950s were 405. the newer one 625. This is 625, which was on the UHF band, which I believe you'll still find some digital TV signals. I'm not sure. I'll have to ask somebody who actually knows. This is the peak white. This is the brightest that it'll go before it clips. So P here is actually the peak white. From this level here, there's a little gap in here, which is called a blanking level. You see the dotted line? That's saying nothing should go below that. Now, when you have a colour signal, this is a black and white signal, you'll find that there's a chroma burst in here. That is something you won't see here. But what we will see is the signal coming in from the camera when we look at the board in a minute, and we'll see one of the first things we do is strip it off, remove the colour information to leave us with a black and white signal, because all we want is the black and white. So that is a basic video signal. We've just looked at the line sync pulses. You can see them to either side here. In the middle we have the frame pulses and the blanking, and this is where the spot returns from the bottom of the screen up to the top again. Depending on the system, particularly with closed circuit televisions, these seem to vary a great deal. You'll sometimes find one great big pulse instead of 5 and this sort of thing. But these, as you can see, are much wider. Field blanking in the book here, it says it's 20 lines. That's about right. So you would have 20 of the line syncs we've already seen for every field blanking period, and that's it. So we can see some of the these, in fact, are the field sync pulses, the big ones at the bottom. They're the, or frame sync pulses you can call them, and they are much bigger, as you can see, than the line sync pulses. According to this, they're 27 microsecond each, with 5 microsecond in between them. But that's it. So that's really how a video signal is made up. It's made up of lots and lots of line sync pulses and these frame sync pulses in the middle, in between each frame. Here we have what most people recognise. This is a line pulse from a composite video signal. This is the line pulse, this is a line pulse, and this is the video information. Obviously a lot of people will be familiar with this, so we'll quickly talk about it. Remember, each line on the television screen consists of one of these, so that's from left to right. We're actually looking at the picture information there. If we expand this a little bit, this here is the colour burst carrier frequency, which is 4.433619, and that is there to synchronize the color. Now, we don't need that, but this is coming from a color video camera, therefore we have to lose it. The pedestal here is where the black level is a bit high, but it's alright. It's coming straight from a commercial camera, so I can't blame anybody for this other than the manufacturers, but it doesn't really matter that much. And of course your peak white would be as high as this will go above that level there. Could be 0.7 of a volt. Is that normal? It's 0.3 for the sync pulses, it's 0.7 above, but there are some systems that will still give you a volt above the line. So that's it again. Now if we go and say, well, okay, that's a line, let's look at a frame. So if we now go back, now we're looking at the frame pulses. They're a bit dimmer on this because it's only coming up every so often, if you can picture it. We're blanking and then we're coming back to these. These are all blanking pulses along here. These are the frame sync pulses there. There's 5 of them there. It depends on the system. Some may have less than 5, some may just have one big one. It all depends on the system, but this is probably what you would say will be the customary way of doing it. And of course, if we move along here, you can see the line syncs are starting to appear. So these basically are blank. This is when the spot returns to the top of the screen, the left hand side, and you can see, there we go. And those of course are all line sync pulses in there. And these are whole frames. On this probe here, we will now put it on the output pin. As I said, this normally, if this was going to drive a phone line, this output would drive a modem chip, and the modem would then be able to go down a telephone line, and you'd need a modem chip at the other end, or a modem proper, to decode it and then feed it onto the receiver. So if we look at that, you can see that compared to the video information, this is really slow. This is 9600 baud. That's the rate at which we are transmitting down our twisted pair. So it's interesting to note how little information you can include from that compared to how much information must be here. If we obviously advance that, there's almost nothing to see at all. Just a quick glance to show what we're doing. Remember, this half is the receiver, and you can see our scope probe is just this side of the socket, and this socket with the yellow plug in it goes off to the monitor. So what we're going to look at now, the next thing you'll see on the scope, is actually what has passed through the entire system and is coming out of the video, out of the receiver. Here we go. This is the scope probe connected to the receiver. The transmitters we have nothing going to at all. And this is actually what is going out to our monitor. Do note that there is no colour information, there's no colour burst there either. So what we'll do, this is quite interesting. There's not a lot of things, once again, because it's all the digital processing we can't really see on the scope, it doesn't mean a thing. But what we'll have a look at is we'll have a look at the output of the digital to analog converter, which is a 7529, and look and see what that looks like. So if I put that on there, and hopefully that works, there we go. Now that is, there's no sync pulses on this at the moment, as you can see. This is simply the same information on there. So basically, remember, that is what's going out to the monitor. That is what is coming out of the digital has fed into the digital side of the D2A, and that is the analog coming out. So that now has to be fed into the information from the sync pulse generator and combined to mix the syncs with the picture information to give us the final one there. So this here is this is the startup screen when you boot the receiver. If I press the reset, it clears the screen and comes up with two grayscales, and there's a different resolution in this grayscale. I noticed from this, I think this is 256, this is 16 bits grayscale. Yeah, 16 levels, so it's 4 bits. Right, all we do now is we'll wake the thing up. So when I press the reset on the transmitter, you'll see how long it takes to do a whole screen, and hopefully we'll have that picture on there. So this is transmitting at 9600 baud, and that's what's going across the twisted pair. Once it reaches the bottom, it refreshes and starts again. So if I put my hand in front of it, you see it interrupts the beam. There is in fact another version of EEPROM, which is version Rev 1.3. I've tried it and it actually works and shows if there's movement in say a compound, if you had it pointed at a compound, and if there's any movement in it, it goes back to those lines straight away. It doesn't bother about refreshing the whole screen. Remember that this entire thing was written in machine code. This is just 2 sheets out of it, but it's all machine code, the whole thing, which is once again quite an art form, isn't it? It's not assembler, it's the next level down. Okay, so let's have a look, and what I have here is a book with 555, 556 timers. If I pop that in front there, it'll show you how bad the writing is. So you can actually see it's not good, but then on the other hand, for resolution of 161 by 69, what do you expect? There you go, that's the first of our extreme projects. If you have any questions, please feel free to ask, although I'm not quite sure how good I'll be at answering them. I have all the documentation on it, and it works, yep, but thanks for watching.